Hello, ladies and gentlemen. This is your daily dose of Dorfler here for section 3 of chapter 15. And yes, I think that might be my new intro moving forward, a daily dose of Dorfler. I thought of it this morning, and why not? You got to have one of those, those catches, those hooks when you're doing these YouTube videos, right? Especially if you want to go off and be one of those influencers. That's a thing. Anyway, section 3 is the last section in chapter 15, and we are going to do it in one video, okay? There's no math in here. I told you there's that very limited math in this chapter. Really what this section is all going to be about is terminology, okay? So we've been talking a lot about different types of waves, and now we need to see how, when waves move, what happens to them when they encounter objects. And the object should be, a wall, a small opening, even going from one medium to another. And so that's what we're going to be talking about today. How do waves in general, what happens to them when they move, okay? And so we're going to start off by talking about reflection, diffraction, and refraction, okay? Say that 3 times fast. Reflection, diffraction, and refraction. I'm not going to say it 3 times fast. That's for you. Anyway, when waves are meeting boundaries, when waves move through a continuous medium, they can either move in straight lines, much like what we see in the ocean. When waves are moving in the ocean, they all look like they're in a straight line. They can spread out in circles. If you throw a pebble into a pond, you see that where that pebble lands in the pond, that those ripples go out into spheres or circles. And then the spheres are reserved for sound waves in air. As I'm speaking, we are starting this going in all 360 degrees, okay? If you're on the ceiling right now, you'd be able to hear me. Out wide behind me, you could hear me, okay? That means that sound waves are traveling on all 360 degrees when I speak. That's why it's a sphere. When waves meet boundaries, they can bounce or even bend in a couple different ways. They can do this when a wave passes the edge of an object or passes through an opening, much like what we see right here. When they bounce against a wall, they can revert back and head back in the opposite direction. And then in a slide, very shortly, you can see where there's a small opening, and we see water waves go in there and what they do once they enter that small opening. Or as I mentioned at the start of this video, waves can bend or bounce when they go from one medium to another. You'll see that a lot of times with glasses full of liquid or, in swimming pools oftentimes. So that's what's happening. These waves are going through different media, I should say. Let's talk about reflection. Okay, we all know what a reflection is, right? It's defined as the bouncing back of a ray of light, sound, or heat when the ray hits a surface that it does not go through. So, reflections of light can create a mirror image of an object, much like what we see here in this lake here. The water waves are going to reflect off of the side of an object, and a wave hitting a boat, for example, and being reflected back in the opposite direction. So we can have water waves be deflected from an object like a boat, or we can have light that is going to be bouncing back when that light ray hits a surface that it does not go through, okay? A lot of it depends on the angle with which the lighting source is, the object to the substance that is reflecting it, okay? There's a few things that kind of go into that whole scenario. Diffraction now is defined as a change in the direction of a wave when the wave finds an obstacle or an edge, much like an opening, as we see over here on the right-hand side. Okay? There we go. All right. Bending of waves as they pass around obstacles. As the wave passes the edge of the object, they spread out as if a new wave were created. So, like if you see here, we've got just kind of like a block, it seems like. We have waves approaching this block. We see them hit that block, and we see there's really no wave activity right directly behind the block, but as the waves continue, they essentially almost reform back together, so that bends around there. When they have little openings like this, the waves are going to bend around the opening, and see here, these ripples right here, right where the yellow arrow is, that's indicating where the original waves are, they hit this, and now it looks like they have a brand new. So it's almost like they have these straight waves like we see in an ocean, and then we see these circular waves once it goes through this tiny opening. The amount of this diffraction that a wave has is going to depend on two factors, that is wavelength and the size of the barrier or opening. Sound waves are a good example. When you're talking and they have to pass through a door, the sound waves travel in a straight line until they reach the door, and once they reach the door, the sound waves are going to bend through the opening of the door and spread out or diffract into the space behind the door. The rock and water waves, hold on, nope, I want to go back. Okay. For some reason it doesn't like when I click on my image here. It likes to kick me out and not be able to see stuff. Rock and water waves. Rock and water with waves. How about that? Waves travel in a straight line until they reach the rock. After they pass the rock, the waves near the edge bend and spread out or diffract into the space behind the rock. Okay, so we saw those two examples up there on the right-hand side. Refraction now is the bending of a wavefront as the wavefront passes between two substances in which the speed of the wave differs. So when waves travel through a new medium, they slightly bend because of a change in the wave speed. So a spoon's broken appearance when placed in water. If you see this image here, my foot is stuck. See this image here on the right-hand side, the spoon appears to be broken in half. That's because the bending of the light waves make it appear as though the spoon is split into two different pieces. Again, we have a medium of air, which is this piece. It's where it's located, and liquid, which is where this portion of the spoon is located. So light waves, which reflect from the top of the spoon handle, pass straight through the glass and into our eyes. So that's what looks normal. However, light waves, which reflect from the bottom part of the spoon, start out in the water, then pass through the glass, then pass through the air to our eyes. So the spoon is going to appear broken because one set of light waves is reaching your eyes from one direction, and another set of light waves are reaching your eyes from a different direction. So they're coming through different media, and so they're going to be passing to you at a different direction, meaning we get this optical illusion. Oftentimes, when we have multiple waves in a certain area, we're going to have what's called interference. Now, there are different kinds of interference. Well, first of all, interference is known as the combination of two or more waves that is going to result in a single wave. When several waves are in the same location, they combine to produce a new wave that is different from the original waves. Okay, waves can occupy the same space by combining into a single wave. So some examples of wave interference from two water waves, as we see over here to the right. As the waves move toward each other, they begin to combine together to form one wave. This new wave that forms moves in a different direction than the original movement of the two waves. So as you see here, we've got the center areas right here where these waves are going to occur. And you start to see that where these waves kind of interfere, we get different patterns here, and they seem to form a single new wave. We see a lot of this ideas in like wave pools. If you ever go to Knights Action Park in their wave pool or any other wave pools, you'll start to see something like that happen. You have constructive interference, which is a superposition of two or more waves that produce an intensity equal to the sum of the intensities of the individual waves. So basically, you get a much larger wave when they combine, or at the instance when they overlap. They reinforce each other. So if we have two waves on a rope moving towards each other, as we see at the very bottom, one wave has an amplitude of 4 centimeters, okay, and the other wave has an amplitude of 3 centimeters. So here's the 4 centimeter one, here's the 3 centimeter one. They come together, and when the two waves meet, they will construct into one wave momentarily, and has a total displacement, or what we say amplitude in this case, of 7 centimeters. And so they overlap, they combine and make larger ones, but then they continue on their merry way and go back to their normal size of their waves. You then have a destructive interference, okay? This is the superposition of two or more waves that produces an intensity equal to the difference of the intensities of the individual waves. So here we have the quote-unquote formula for it, where if we want to determine the intensity of a wave for destructive interference, we take the amplitude of the highest wave and subtract from that the amplitude of the smaller wave. And when this happens, when destructive interference happens, the crest of one wave meets the trough of another. So when we see down here, we have a crest meeting a trough. So if we, again, back on the rope here, one rope has a crest with a displacement or amplitude of 4 centimeters. So that's this one. And the other rope has a trough with a displacement of 3 centimeters, much like what we saw in the previous example, except this time it's a trough. And as the crest and the trough of these waves overlap, a new wave will form with an amplitude of only 1 centimeter. So they have counter construction with them. So they basically reduce each other whenever they come into contact. Okay. If you have situations where two waves are the same amplitude in terms of destructive interference, they completely cancel each other out. And so that's what this is actually showing you. We have two waves, same amplitudes. One's a crest, one's a trough. They meet together and you get completely flat situation. Let's talk about wave interference occurrences. So rainbows that appear in soap bubbles. We probably all have seen that one, right? The light waves that strike the bubble are going to bounce off the bubble, or the outside of the bubble, and travel directly towards your eye. They're also going to travel into the shell of the bubble, bounce off the inner shell of the bubble, and out the bubble shell back through the air towards your eye. So you got some that are just going crazy inside there, and eventually some of them are going to bounce right back to your eye. The two sets of light waves are out of phase, okay? And they're at different frequencies. So you can have constructive interference, which would produce colors. You can have destructive interference, which would also produce colors. And so we get this swirling rainbow effect. So we have a combination of all of this occurring. We have beats, okay? Beats are defined as alternating patterns of loud and soft sounds. Constructive interference occurs when sound waves arrive at your ear at the same time. So the sound that is going to be produced or perceived by your ear would be louder. If we have destructive interference, this is going to occur when compressions from one sound wave and refractions from another arrive together. So this gives us the sound of softer loudness. And so when we tune musical instruments, we listen for that. If they are out of tune, you're going to hear kind of a woo, 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 woo sound, a slight vibration. If they are in tune, if certain strings, like for guitar, if they are in tune, you'll hear them make the same sound. Okay, it'll be a nice, smooth tone. We then have standing waves. I told you this whole section was about terminology. Standing waves are defined as a pattern of vibrations that simulates a wave that is standing still. Standing wave causes the medium to vibrate in a stationary pattern that resembles a loop or a series of loops. Two waves are traveling in opposite directions when standing waves occur, much like what we see here. When we have standing waves, we have what are called nodes and antinodes. The nodes are where the two waves meet. The antinodes are when the two waves are at their farthest parts, or the farthest amplitudes away from each other. Then we have nodes, antinodes, like I just mentioned here. They are the points where there are no vibrations that separate each loop in a standing wave, points at which crests of original waves meet the trough of reflected waves. And so these are points of destructive interference. Antinodes are going to be, well, just the opposite. That's what anti means. They are points of maximum vibrations that are midway between nodes. These are points where crests of the original wave line up with the crests of a reflected wave, and are points of constructive interference. So, went through that relatively quickly, like I mentioned. Also, that is it for Chapter 15. We will have our test before leaving for Thanksgiving break. Most likely it'll be the 23rd, which is also going to be the same day that your test review will be due to be submitted to Google Classroom. So, again, if you need to watch this again or pause at any moment, pause it. You have the power at your fingertips at home. So, with that being said, we are going to end this daily dose of Dorfler. If you have any questions, you know where to reach me. Have a good day now.